the pH of a solution obtained by mixing 50 ml of 0.1 molar sodium hydroxide with 25 ml of HCl? Sodium hydroxide, strong base, HCl, strong acid. What's your net ionic equation? H plus hydroxide gives you H2O. What's the KEQ for this? 1.0 times 10, 0 times 10 to the 14, a very large number, right? So what's our initial concentration? Okay, let's just do moles first, and we'll figure out concentration later, because we know this is going to go all the way, right? So let's just do moles. 50 mils times 0.1 is how much? 50 mils times 0.1 millimoles per mil. That's 5 millimoles, right? So that's 5 millimoles of HCl, sodium hydroxide. So your hydroxide would be 5.00 millimoles over the total volume, which is 50 mils, which is 75 mils. The total volume is 75, so over 75 mils. That's your initial concentration. Okay. Molarity times volume gives you moles, but if you use milliliters, that will give you millimoles. What's the initial concentration of HCl, of H plus? 25.0 milliliters times 0.100 moles per liter. That gives you 2.5. Okay, liter cancels out, so that gives you the answer in millimoles. So initially your H plus is going to be 2.5 millimoles divided by the total volume, which is 50, and 25 is 75 mils, right? So those are your initial concentrations. And we don't worry about water, we got tons of it, right? No, not tons, plenty of it, excess. What would be your changes? 2.5 versus 5, 1-to-1 ratio. Which one is the limiting reactant? This is your limiting reactant. Right. And this KEQ is very large, so you know it's going to go all the way, right? So you're going to have trace amounts left here, right? So you have, okay, you're going to pretty much lose everything here, minus everything, right? Right? And how much do you have here? You're going to lose 2.5 millimoles over 75 mils, right? In other words, the amount you lose would be minus 2.5 millimoles over 75 mils for HCl, for H plus. So at equilibrium, you would have virtually nothing here. It's a trace amount, okay? And we're just going to call that X, so we can figure out what that is. So what's 5 minus 2.5? So this is going to be 2.5 millimoles over 75 mils. Okay? And water will just be excess, so you don't worry about the water. Okay? So, in other words, what we're really saying is, assume it goes all the way and then back it up a little bit, okay, so that you have a trace amount of H plus in your reaction mixture. Okay, in other words, this is really going to be there's going to be a plus X here. Okay, if there's X amount left here, then there's going to be a little plus X here, but this extra X will be negligible compared to this, because that's just a trace amount. So H plus, okay, so we're going to say then what? 1 over X times 2.5 over 75, right, is equal to KEQ, which is, because water is in your activity of water is 1. Products over reactants. H plus and hydroxide are reactants here. So you can say that's 1 over KW. Or you can also say, so this is H plus, and that's your hydroxide, is equal to 1 over KW. Okay. Or you can say, if you take the reciprocal, you can just say X times 2.5 over 75.0 is equal to KW. So I can solve for X. What's my X going to be? Yeah. So now, what do? You say 75 times 10 to the negative 14 divided by 2.5. That's 3 times 10 to the negative 13. Okay, so 3.00 times 10 to the negative 13. That is your H plus, right? Okay, that's your X. That's the trace amount of H plus you have left. It's a very small number. Okay, what would be your pH at this point? Negative log of 3.00 times 10 to the negative 13. That would be, take the log of that and then take the negative. That's 1 point. It's going to be 12.5. 3 decimal places, so 12.522. Okay. That's your pH. So, does this make sense? Do we expect to have a very high pH at this point in the reaction? That's a high pH. High pH means acidic or basic? Basic. Do you expect it to be basic? 2.5 versus 5. You have no H, hardly any H plus left. You get a lot of hydroxide left unreacted. Okay? So you can use this type of calculation to solve the pH of your reaction mixture. If you were in the lab, okay, and you were to do in the lab, there's a procedure that you do in the lab called titration, where you have an acid here, and then you gradually add drop-wise your sodium hydroxide to the acid, okay? And if you can monitor pH versus volume of titrant, this is called titration, so your sodium hydroxide is called your titrant, okay? Volume of titrant. If you were to monitor the pH of this mixture, what will happen? You start off with just acid, right? So you start with a low pH, and then the pH will gradually increase, okay? And you can calculate what these numbers, what the pH would be at every point in your titration if you want. If you make a plot like this, you get what's called a titration curve. What you'll find for a strong acid, strong base reaction is as soon as you get very close to the equivalence point where you have equal concentrations of H plus and hydroxides, when you get to the equivalence point, that pH is going to jump to 7. But a drop before that, like 0.05 mils before that, the pH is going to be low. It's something like 4. Okay? And then a drop after that, pH is going to be very high. So if you were to monitor this reaction, this is what you'll find. Okay? So if you use a pH meter in the lab for titration, it's a very good way to determine what's called the equivalence point. The equivalence point in this case would be at pH 7, okay, for a strong acid, strong base. So this is what you would call your equivalence point, where you have a 1-to-1 ratio of H plus and hydroxide mixed. Okay? Now, where are we on this titration curve as far as this problem is concerned? This example that we have a lot of hydroxide, right? And you've already consumed your H plus. So we're way past the equivalence point. So where would we be on this curve? Would be right around here, at pH of around 12 point something. Okay. So this big jump right here in the pH near the equivalence point is a very good way to determine the equivalence point of the amount of acid that you have in your flask by titration. Okay. Now what you can also do is you can add something that would change color when the pH changes by this much. And in the lab, the typical it's called an indicator. The typical indicator we use in the lab is called phenolphthalein. Okay. And phenolphthalein changes from colorless below pH 7, and it changes to pink above. Actually, it changes at around 9. Okay, but this one is a big jump in pH from around pH 7. So that's called a titration curve.